Well, let's see. It's late at night where I am, but I thought I would. Was about to do some programming, and I thought, what the heck? I will log in here and do it with anybody who wants to watch in the Twitchverse. So here's what I'm trying to do. I wrote this very big book that came out in 2002 called New Kind of Science, and it was all based on doing computer experiments. And the So there are all kinds of interesting pictures in the book and so on. And I thought, wouldn't it be nice to have some Wolfram notebooks that just do what's in all these pictures? And actually, the way they were created was with Wolfram Language, or as it was then mostly called Mathematica. And I have all the notebooks that created these, and most of them were created. It took me about 10 years to write the book. I started writing it in 1991. And so these things in the early chapters were mostly created in around 1991. And so I just started last night, actually, taking the old notebooks that I had from 1991 and modernizing them. And it turned out they didn't take a lot of modernization for these ones. And for example, here, let's see if I can find it. I should have someplace here. I should have a sample of what I did for this last night. Here we go. This is page 25. So page 25. This is the notebook I made from page 25. And so you see nowadays making that picture, it's really easy, and that one too, it's really easy. So I thought what I would do today is try and do this for a few more pages. And actually what I'm going to do is associated with every one of the main text parts of the book, there are a bunch of notes in the back. So I probably have, let's see, I have on my desk here, let's see, well, there's the actual book, and I thought, here, I'll take, there's lots of cool pictures all through the book, but I thought I would take some pictures that were associated with this chapter 2, which is called The Crucial Experiment, and I thought I would try and reproduce some of the pictures that are in the notes for that chapter. So let's go back here, all notes for this section. So I think it said here, implementing cellular automata. Okay, so I'm going to, let's go ahead and make a notebook here that's going to be just called, it's in section 1. Actually, it should be in the notes section for this. So I should create, for chapter 2, I should create something called notes. And let me go ahead and do that. And then let me create a first note here that's just called implementing cellular automata. This will now be where I'm going to put all the material. So let's get going here. So that first image there, I can create that very easily. So I just say array plot of cellular automata. It's gotten a bit easier over the years to do this. And it's rule 30, and I am doing it for 50 steps, and there it is. So that one was super easy. Let's see, I've got a bunch of other stuff here. This is kind of a weird section because I'm actually talking about implementation right in that section. So maybe you know what, I'm going to move on to a different section here and try to, let me not do this, let's do this one here. This one looks like a nice one. So let me go ahead and close that, make another one. This is called mathematical interpretation. Of too many L's, cellular automata. Okay, now let's see if I can reproduce this picture. Now I'm going to cheat a little bit because I'm going to go back and look at my old code from 20 years ago and try that. Hold on, let me see here. I need to go find that material. And I've got a whole pile of, let's see, no, that's not what I want. Let me, I need my pretty well organized material from a really long time ago that I thought I had here. Oh yes, here we go. So this is my old book construction notebooks. So I would reckon this was chapter 2 notes. Okay, so this is my really old. This was made when screens were a lot smaller. So let me see. This is this was all right. Let's take a look at CA maps. That was this one here. Okay. So here it is. I could just run this old code actually, but I know I can do it better now. So what this is doing is it's showing for a cellular automaton, which is so I had an example up here of a cellular automaton that shows here's the rules and here's what happens when you apply these rules repeatedly. So this is a picture that shows. Let me take a look at how far across that is. So this will be all right. This is very okay. It would probably still run, but it's not the best way to do it these days. Let's say we can make a cellular automaton which is applied to integer digits of n, 2, and I don't know quite how big these are. This seems like it might be, okay, it's size 12. Okay, so this is going to be, let's say this is rule 90, for example, and I'm going to try just seeing what happens with this. If I say, let's pick a random number here, okay, this is a good sign. And so that's going to say, given this cellular automaton, rule 90, applied to this state, which is integer digits of that, the cellular automaton would generate this output. And I can turn that output into just a number, so I can say from digits of that, 2. Okay? And now for each of the numbers here, I can make essentially this map that says what the cellular automaton from all possible initial conditions from let's say 0 to 2 to the 12 minus 1, I can say what that cellular automaton will turn into. Okay, so they're all the results. And now if I say list plot of that, and I think I need to say aspect ratio, because I'm just going to copy what it said from the other side. I'm going to say aspect ratio to automatic. Then I should get a picture. And isn't that cool? The picture I'm getting there is exactly the same as the picture I got there. And let's try and make it even more the same. Let's say frame arrow true, ticks arrow none, and I should get, oops, what did I do wrong? Oh, I put a dash instead of a greater than sign there. Okay, so now I've got a picture that's very very similar. I'm going to make it even actually, yeah, actually I want to say frame ticks is none. Okay, that looks pretty much the same as what I got over here. So these are for a bunch of different cellular automaton rules. So let me go ahead and do that. And then I'm going to say for each of these, so for each of those rules, I'm going to go ahead and say there, and I'm going to also put a label on the plot to say which rule it is. Plot label. I really could make it almost exactly the same by having a string template and then saying just rule, and then what that rule is, comma, hash sign, and let me see whether this will work. And then, oops, no, I want to do this. Let's see what happens if I do that. Okay, there we go. So that's now to be compared with these pictures over here. and I think we succeeded in doing our first example of reproducing what we had in the book. So that's a there it is. Okay, so that's our first result. So that will be connected to this page here. All right, let's go on. See if we can do the next page. Okay, that's showing something different. We won't do that because it isn't a picture. We'll just do the ones that are pictures. Okay, here we go. Here's another picture. Okay, so this is called another. It's very satisfying actually doing these, because it's like I'm taking things I did. This must have been 1991, and I'm kind of redoing them, and it's I think it's a lot easier than when I did it in 1991. Okay, let's take a look at this now. This one is the next one of these pictures, so that will be Rule 90. Oops, it was called Rule 90 Alt back in the day. So here's an old notebook. This notebook works just the same now as it did back in 1991. I made this in 1991. Okay, so here we go. So here's the old notebook, and as a matter of fact, very conveniently, this line will just give us the initial condition for that first picture, and now all I have to do here is that says it's 260 steps. So all I should have to do is to say cellular automaton of 90, that, 260 steps, and hopefully. Ta-da! Oh, I should have also tell it to make a picture of that. So I can say array plot and that, and oops, something went wrong. It's the same picture at the top, but what's going on here? So that's oh, there we go. That one was said 40 there. Oh, I see. Okay, so that's the first one there. There we go. So that's the first picture that I have from over here. I just reproduced. So let's go ahead and do the second picture, which comes from that code there. That's setting up the initial conditions. And let's do it again there. And let's say 260 steps. And there we go. So now we just made the second picture. It's got a bunch of nasty anti-aliasing on my computer screen. So I'm going to make this say, I'm going to say pixel constrained, which tells it to just align everything with pixels to true. And now what should happen is, if I make this, oh no, let's make it two pixels per thing. That got a little bit bigger, but that's kind of, there we go. So there we reduced these pictures. So that's the same as what we had in the book, except now they're larger, and that's another page done. Okay, let's keep going. We're on a roll here. Okay, here's another page. So let's go ahead. This says more colors in additive cellular automata. So let's just call it. Okay, we're going to save these away. So these will appear eventually in. Okay, so let's call these. That was called more colors in. Let's just call it just more colors. And now we're going to look at what I did 20 years ago. Let's see whether that's instructive for this. And here we go. Interesting. Okay. Right. Fair enough. Okay, I can use exactly the code that I used before. So what this is going to do is, what this does is it takes a step. So let's go ahead and do that for the case k equals 4. First of all, let's just put in a 4 there. And now I want to say nest list. And then I think what I'm going to want to say is center list. And how big are these? I wonder. I'm sort of saying, oh, 2 tmax plus 1. So that's 101. So let's say, oops, this should be center array. And that should be a 1 in there, and 101, and then 50 steps there. And I think if I do this, there is a good chance that it will look like one of the pictures that we have in the book. Ta-da! Okay, so it looks like that picture there. That's the case k equals 4 there. So I might want to label it plot label. Again, I'm going to say a string template to say k equals, and then I say for the value there. And now what I want to do here is, actually I have to do something a little tricky here. I have to make a function that is going to look at the number of colors, k, and put it there. And then I'm going to put it also here. And now I want to close that up. Did the wrong thing here. I want to put that outside the array plot. And I hope that this can now be just so I've got numbers 2 through 7. So let's give that a try. Okay, so I just produced these pictures here, which encouragingly enough look just like the ones in the book. So again, another nice success. Actually, I could make these. I'm just going to make them just out of my own curiosity. I'm going to make them a little bigger. So I'm going to say image size arrow. Let's just say medium. And now, oops, what did I do wrong here? Oops, wrong place. That was in, I did something very goofy there. I want to put those inside there. Okay, so that's just making the pictures larger. I think it looks better larger, so I'm gonna just leave them at that larger size, and I'm not going to I'm not going to include the ones with the smaller size. Okay, so we did another page. All right, let's keep going. Okay, that's another one. All right, let's see what we do for that one. Okay, so this was, wow. Okay, that looks like it's connected to the wrong picture, actually. You know what? That's a bug in the that's too bad. That's a bug in this. I am going to take a screen capture, and I'm going to send a piece of mail that says that's a bug. I wonder how that happened. It's probably when the book was converted, those wound up on the wrong page. Anyway, so let's go to this page. That is other integer functions is the name of that page. So let me go ahead and say other integer functions. And now I want to go back here, and I'm going to go figure out what these were. And now I go back to my crib sheet over here from my code from 20 years ago. Other functions. Okay, interesting. Well, this is actually giving me pretty much exactly what I have to have for this. And this is actually, I can just take this code right here and use it. So I could take that code, and I could say, in fact, I can take this code here. Oops, I just click on this here. Take that code there, and I'm just going to say this. Use that code, and then I'm going to say, let's see, I'm going to say array plot of that. Let's see what this does. Ta-da! Oh, one bug. I didn't tell it that I wanted to give, actually what I'm going to do here, I'm going to do this. I'm going to say that's #1, and then I'm going to say plot label. Actually, I'm going to do this differently. I've decided I'm going to do this differently. I'm going to do each one of these separately. I think it's clearer to do that, and we don't need to combine them together like this. So I'm just going to say mod of the first one, which is binomial mn. I'm just going to say mod that, and there we go. There we go. Okay, that's the first picture. Now I'm going to make the second picture, which is a multinomial. So I'm just going to replace the binomial by multinomial here. Okay, now I'll make the third picture, which is replacing that by a sterling number of the first kind. Okay, there's that picture, and let's do it again. And now we'll make it with a Stirling number of the second kind. And now we've reproduced those pictures. So, another page. Okay, so let's go ahead. Actually, I could, just for fun, I could make that be a picture with 100 by 100 rather than 50 by 50. It might look nicer. Let's just annotate that with more steps or more values. Actually, I'm going to make it 200. Actually, just for fun, I'm going to make it 256 because I have a suspicion that powers of 2 will be interesting. Well, not terribly interesting, but that's kind of an interesting fractal, distorted fractal type of thing. Actually, I'm going to do the more values thing up above for that, the one above it as well, because I think it'll look nice. And that was a Stirling S1, and there we go. So those are distorted Sierpinskis that we got out of those. All right, on we go. Let's go on to the next page. So these look fun. So this is a page called bitwise functions. Okay, and now let's see what we had from my very, very old code about this. It's called bitops. Okay, let's see what that looks like. Open up bitops 2D. Okay, well there's that first piece of code. All right, well I can see what it's doing. It's a little bit messier than I would do it today. This is using bit and bit XOR. So let's see if I can do this. So it had a reverse in it. I don't know quite why it needed that reverse, but we'll find out in a minute probably. Let's put the reverse in there, see whether that helps. I don't think it needs that reverse. I think that reverse is unnecessary. So let's say, so this is making, so bit XOR or bit AND takes the binary bits of a number and it will combine two numbers in terms of their, by just looking at their binary bits. And there we go. Now I noticed that it had that thing in the top right corner, and I have no idea why that was important, but I can achieve that by just doing what this did and putting a reverse in there, and now that black part will go in the top right corner. Okay, so we got our first picture here. Let's go ahead and do the second one. So that was bit OR instead of bit AND. Let's try that one. Okay, and the next one was bit next one was bit XOR. Let's try that one. Okay, great. So now the next thing was the 3D versions of those. So that may have been, okay, I see what's happening here. Okay, so we did that in terms of cuboids before, and I'm guessing I can do the same thing again. So let me just see whether I can run this old code. Oh wow, it's the whole thing would just run actually, but I'm going to do it slightly differently. Let me see. What this is doing now is saying make a cuboid. Okay, so actually this is, let me say at the top, let me put a heading here, 2D patterns, and then I'm going to put another heading down here, 3D patterns. And so now here, let me just see what happens if I do this. So I'm going to say graphics 3D of those cuboids, and here I'm going to say bit AND of X and Y, and ta-da! Cool. Okay, so there I've got my lovely 3D. This is pretty neat actually. My 3D picture of this. Okay, I'll do it again. There we go. Okay, this is fun. Alright, so that's the 3D picture, and the old code basically just ran. I mean, it would run, the whole thing would run, except that it would just be using old-fashioned graphics primitives that won't look as good. Okay, so there's bit OR. So what that's doing is the height of every thing here is the bit OR of the coordinate position. So let's try bit XOR now. I don't know. Okay, so there's bit XOR. So that's actually, yeah. You know what? I'm going to put a heading up here because we're going to have several other things on this page. Okay, let's try. I think these are. Let's make that heading bigger. Okay, 2D patterns, 2D 2D bitwise operation patterns, and I'm going to say then 3D bitwise operation patterns. And then down here I'm going to say this is quotes munching squares, because that was the name that was given. Oh yeah, I say there that it was called munching squares. Oops. Okay, so now let's go ahead and see what the code for that looked like from ancient times. Okay, it was called munching there. Oh, that was very easy. Okay, trivial. Alright, let's just pick up that code. And actually we did, wow, the exact code will just run. Let me, I'll make one change because I think I can make it look better. I'll call that array plot. And ta-da! Oh great, it says graphics array is obsolete. Switching to using graphics grid. Okay, thank you very much. Okay, there we go. So that's the exact thing we had before. Now actually I think in the previous one we had put in little mesh lines, so let's go ahead and put those in as well here. Mesh arrow all. Okay, there are the mesh lines. There's the exact same thing. So that was cool. We could just take code from 25 years ago basically and just run it. Just for fun, I'm going to do a larger case here. So instead of 15, I'm going to say, instead of the 8 there, I'm going to say, let's say, let's do 16. And then let's say there, kind of living dangerously because I don't entirely know what I'm doing here. When in doubt, don't modify the old code. Let's do 31 there, and let's get rid of the mesh. And let's try that. I probably want to say partition there in things of 8. So let's try this. Okay, so that's just a larger version, same deal, but it's just showing it for a larger region. Okay, so let's just annotate larger region. Oops, larger region. There we go. Okay, well, let's look at the last thing there. Bitops 22, what was that? Okay, so that's showing, what are we doing here? That appears to be showing the, what's this doing? So, Curb's applying bitwise functions to n and 2n for successive n. Oh, I see. So what this is doing is, we could call this bitwise shift functions. So what it's doing is it's saying make a table of bit, let's say bit and of n comma 2n. N goes up to, well there it seems to be going up to 256. And make a table of that and make a list line plot and then make that be filling, so it will fill to the axis, fill to the axis, and then let's say frame is true and frame ticks is none. Let's see what that does. Okay, cool. So that's making essentially that first picture there. It's a slightly different aspect ratio. I don't know if we want to reproduce that aspect ratio. Let's see what the aspect ratio was here. I think I may have just had that aspect ratio because, where was it? Aspect ratio 1 over 2.5. Okay, so I may have just had that aspect ratio to make the thing fit well in the book, but let me put it there just so we reproduce the same picture. Okay, there we go. Okay, so that's that one. So let's now do the next one, which was bit or, but that was going up to 512 instead. So here we do bit or, and here we go. You know, this thing at the end is a goofy thing, with the fact that we should only go to 255 there. and that one should only go to 511, so it won't have that little weird jump up at the end. And actually it should really go from 0 to 255 and from 0 to 511. And then this one, next one, should be bit XOR, and there we go. Okay, that all just worked. Okay, so that's that. That's that page. Let's see, the next page we have, oh, wow, okay. That is going quite a long way there, okay. Well, let's see whether we can just use this. So that is looking at my all-time favorite cellular automaton, Rule 30. I have to make a picture of Rule 30 because I have it everywhere. It's like on my business card and everything. So Rule 30 makes this kind of pattern. Let's make it the pattern here. Makes this kind of pattern. And the big deal is, if you just look down the center column of Rule 30, what's the sequence of black and white squares? And the point is that sequence of black and white squares is really random. So this is talking about the center column, and it's talking about whether there's an excess of black over white squares in the first million. Let's see. This is the first 100,000, and that's the first million. So I wonder whether I can compute that immediately on my machine. I think that we may have put one of these in our data repository as something that has already been computed. And let me try and see that. So let's take a look here. 1 million bits of the center column of Rule 30. Okay, so that's a place where this was already computed. And I don't know how long it takes to compute. We can just try. Okay, so this will just read it in from our data repository, and so I could just say data equals this. I better not tell it to print it out because that will be very okay. So now it's just reading it in, and there it read it in very quickly. So let's see if we can recompute this. So the way we'd recompute this is we'd say cellular automaton of Rule 30 started off from 1 and 0, and then that would be the 0th column, and then we would probably say flatten that out. Oops, no, what I want to say is let's say 100 steps and the 0th column. So let's try this, see whether that does the right thing. Okay, so that should be the center column of Rule 30. So let's go ahead and see whether it looks right, just to check I did the right thing. 110 111. Yep, I got the right thing. Okay, so there's what we got, and now we can go ahead. Let's see what this is computing here. Actually, what I want to do, let's look at this. The Rule 30. Let's see, random walk. Okay. Oh, that was boring. Okay. Well, actually, what this did, it actually computed it right then and there. And let's just see what that does. So let's call this direct computation. And let's go ahead and say with n equals 100, for example. Let's just see what that does. Ta-da! Okay. Does it give the same result? Let's see. Well, I see. It's off by 1 because it didn't have the 101th place. Okay. But anyway, let's also say here data repository. That's just another way to get the same results. Okay. So let's go ahead and see what that thing was actually doing. So we take that and we say, okay, okay. So what that's doing is it's going up every time. What the heck is that doing? What's that doing? I don't know what that's doing. I mean, I can read the code and I could just run it, but I want to understand why it was done that way. I kind of think that might be... Oh, I know what that's doing. That is pruning out the number of actual points to plot, because this was okay. So let's anyway let's do the thing to compute this as kind of a random walk. So we can say 2 times that minus 1, and then that will be plus 1 and minus 1, and then we can say accumulate that, and that will just accumulate this to make kind of a random walk. And now we can say list line plot, and let's see what that looks like. And that should show us kind of a random walk. And I think that other thing had filling to the axis, so let's put that in just to make it look nicer. Okay. Alright, so that was 100 steps of random walk, so let's do 1,000 steps. Okay, that's what it looks like at 1,000 steps. So let's go ahead and do what it was doing in the book, which was, what was it doing in the book? Did I just get rid of the book there? That was stupid. Okay, let's go back here and let's get it again. And here we go. That was chapter 2, and that was somewhere around here. And let's go notes. I guess that's down to rule 30. There we go. Okay, so what do we do here? So that was 100,000 steps. So let's do the same thing I just did here, but this was 1,000 steps. So let's go ahead and try. Let's not live quite as dangerously yet. Let's do 10,000 steps. Okay, and then let's do, actually that was really nice and fast. Wow, things have gotten a lot easier in 25 years, you know? 100,000 steps. Well, that's not quite as fast. Okay, there it is. Now, let's compare that with what I had in the book. And let's see if it looks the same. And yes, it does, except the aspect ratio is different, because that one is sort of more dragged out. Let's make the aspect ratios the same by going and looking here what the aspect ratio was set to be. Oh gosh, this is a book list plot. I have no idea what a book list plot did. Well, let's see. Let's just try for this one whether the aspect ratio happens to be 1 over, let's see if it's 1 over 2.5. Well, maybe, maybe not. And let's put that in the other ones. At least it looks closer. It looks pretty good. Okay, so let's do that. There we go. That one takes a little bit longer, so it's beginning to strain itself when you get to 100,000 steps. So I think what we're going to do is, actually I'd be curious to see how long this takes for 1,000 steps. And we can do the exact same deal we're doing here. We can say 2 times that minus 1, and then we can say accumulate that, accumulate that, and then we can do the same list line plot thing. And just to show an example here, and then like this, and let's see what that does. Okay, so that's now running just for 1,000 steps, but using this direct computation directly right here in the code. Okay, so this is data repository. So now I can take that same list line plot. This is right here, that's the million bits. So I can probably say this is going to be a little bit more time consuming, I think. And I don't know what it's going to do when it tries to plot them. Let's see, accumulate that minus 1. Okay, we are living a little bit dangerously here. Oops, I forgot to save this, didn't I? That's terrible. That was just called Rule 30. Very simple. It would have been bad to not save this. Okay, and now let's see what happens here. I'm now going to try doing this, and it may be horrible because it's going to try and plot 1,000,000 points. And I don't know whether it's going to have the sense to downsample those, and maybe when in doubt read the documentation. So why don't I look at the documentation for list line plot and find out how to do downsampling. So let's see what it does by default. So it's all kinds of stuff there. Alright, so this is going to show us, I'm guessing that there's a thing. Okay. Well, it doesn't seem to say that, how it does that. Let's see, maybe there is something here that plot. I would have expected a thing called plot points or something to do that downsampling, but let's go ahead and try it. Just try running this. I may regret this, but let's just try it. Okay, so it's trying to render 1,000,000 points there, and that I think is what my other code was doing. Was it was basically downsampling. Yeah, I don't think this is a good idea. Let's kill that. Wake up, computer, come on, don't do anything horrible here. Maybe I should look at what the examples here showed. Okay, that was just taking the first 100,000 elements of that. That was kind of boring. Let us try up. Oh, no, yes. Wow. Okay, it actually plotted it. It took it a bit of effort, but it actually made the plot. And now it's spinning its wheel for reasons I don't fully understand, but at least it managed to plot 1,000,000 points there. Okay, wake up, computer. Come on, wake up, wake up, wake up. Humph. Why is it spinning that wheel like that? It's kind of a weird thing. Okay, oh, it finished. Okay. So actually, let's try and see whether we can click on that. This is where it's going to be in trouble, because when we try and save this file, this thing is going to be absolutely huge, because it's saving this plot that has 1,000,000 points in it. So we would have been smarter to use a function like downsample. Let's see if it can. Oh, come on, wake up! This thing is all upset because it's trying to render those 1,000,000 points. And okay, there we go. Now it did it. Okay, so I wonder what happens if I look. There's a function called downsample. Let's see what downsample does. Returns a down by sampling every nth element. Well, that's pretty straightforward. Okay, so let's see what happens if I just say, for this thing here, if I just say downsample this by a factor of, let's say, by a factor of 100. Okay, so if I do that, this should go pretty quickly. There we go. Okay, now the only bug with that is that then the scale is wrong here, because I've been only sampling every 100 steps, so it isn't giving me the full. It's telling me the wrong scale for my 1,000,000. Oh, come on! It's even taking time to delete that monstrous creature with 1,000,000 points in it. Come on, wake up, computer! I know you can do it. Now I just have to figure out how to deal with the fact that this is not that this was oh, come on. I just was telling it to delete that. Come on, you can do it. There we go. Deleted it. Okay. Okay. So now we've just got this problem that the scale is wrong here. So how are we going to deal with that? Well, what we could do is we could say, let's try this. Let's see what is the length of that thing, and let's just try. You know, what's interesting is this. Okay, 10,000. So what we probably could do is we could just say, and this is exactly what my code from 25 years ago did, range of let's say 0 to 10 to the 6 in steps of 100. Let me see if that works. So now I can do this, and so that is hopefully, let's see if I got this right. So if I do that and I say how long is that, ta-da, it's and 1. That's a bad sign, so I probably want to go from 1 here. Okay, so transpose that and the downsample of this, and let's see what happens there. What did I do wrong? Downsample. Oh, I need to close the transpose. Okay, ta-da, there it is. That looks right. Now let's compare that picture with the picture that we had in the book. And the picture in the book, where is the picture in the book? Here's the picture in the book. Okay, it's that bottom one there. And I'm very encouraged. Yes, it looks the same. Okay. So let's just clean this up. Let's see, how are we going to annotate this? That's just right at the top. 1,000 steps. And that was then 10,000 steps. And this is 100,000 steps. And this here is 1,000,000 steps. No, it isn't. That was a different thing. That was just, let's see, alternative computation for 1,000 steps. So let's get rid of the heading here. I don't think that's so useful. And then this says retrieve data for 1,000,000 steps. Okay, what else do we have on this page? So on this page we also have this plot here, which shows something a little bit elaborate. If you look at the picture of Rule 30, wherever I had that, there is, okay, I'll make another picture of Rule 30. So, gosh, I must be typing in this. This must be my favorite line of code at this point. Okay, so let's go 200 steps there, array plot. Okay, so actually let's go ahead and make it be pixel constrained to 1 pixel, but I'm going to make this like 500 steps. Okay, so what you see here is there's kind of a very orderly part on one side, and then there's a disordered part on the other side. And so this line that separates order from disorder moves at a certain rate. And we have this back here, this RW fluct thing. Oh, this is complicated, complicated, complicated. Okay, oh wow. It says this ran on Pion in 67305 seconds. Okay. Wow. This is a bit complicated. Alright, let me pull this code over and let's see what I can do with it. I wonder what that matrix A is. Interesting. Interesting, interesting. Alright, when in doubt, let us just see whether the code of long, long ago just runs. Let me just see here. What was M there? I see. Okay. Alright, let's see what happens here. This is a little bit more complicated than we've done so far. Okay, so let's say, so this is, quotes, random walk of center column. And this stuff here is fluctuation let's see, fluctuations of order chaos, order disorder line, order disorder separator, I don't know what we want to call it. Okay, let's try here. Okay, so now I'm just going to try and run this old code. Okay. And let's just run it. So let's try living super dangerously. Let's just try running diagonals of something smaller, 100 for example. I wonder what that means. Interesting. So that's some kind of thing that, you know, I really hate this matrix that's called A, or whatever it is. Let me just see where that appears. It's there. So let's say, oh gosh. Well, let's take a look. I'm reading this code here. Wow. Yeah, okay. Okay. Interesting. Alright, let's call it, I'm just going to call this A list because I can't stand having something whose name is just A. I don't really know what it does, and so I'm really just hacking here because I'm just renaming the thing from A to A-list just because I feel like it, so to speak. Let's try doing this. Let's say the following is based on original code. Following is the original code used in the creation of the book. Okay, now what we seem to be doing here is, okay, randomness meets periodicity is diagonals data is the second part of that. Okay, I don't really know what the third part of any of this is. You know, what might be, oh, I see. I'm going to guess, well, I'm not sure I know what I'm talking about here. I'm thinking that these things here, let's just take, let's take that R30 boundary and let's take the first element of that and let's do a list plot of that and let's see what all those points look like. Well, that's totally obscure. List line plot. Wow, what the heck is that? I have no idea what that is. That may be the boundary. Yeah, I really don't know what that is. Okay. Well, this is now 100,000. Okay, so let's try and do this thing that took, that seemed to say 63. That is a very scary number of seconds. 6305 seconds is otherwise known as that number of minutes, which is otherwise known as 18 hours. Okay, that's a bad sign. But let's see whether we can, in any case, let's just see what happens if I start running it here. I think I'm not going to know what's going to happen. I'm going to just run, let's run 1,000 of these. Okay, and see how long that takes. That was pretty fast. Alright, let's just try the totally outrageous thing of trying to, let's see, this is probably just going to be a total lose, but let's just try it. Okay, and as it's running, I'm going to try and move over some of this other code. Actually, what I really should have called this, well, let's see if it runs. I'll be amazed if it runs. What on earth is this thing called M? I'm kind of guessing that's the most recent result there and that wasn't correctly done here. Okay, so let's try, yeah, this is kind of crazy because this took 18 hours to run. Okay, so let me make a note here. Took my old computer used to be called Pion, and okay, took 30 on in. I wonder what year that was that this was run. So let's find out when. I wonder whether this notebook actually has. I wonder whether we were doing those yet. A notebook history. Let's see if it has. Nah, no history available. So I just have to look at the creation date for this notebook, for this document. I'm guessing in 1991 or so. Okay, well, I think it's completely crazy to be trying to do this thing with yeah, so that 100,000, I don't know where that's coming from, but let's try. Okay, so this is crazy. The one thing I definitely do want to do. All right, actually, you know what? I've got an alternative approach here. What can I do here? Yeah, I know what I'm going to do. I am going to take, okay, so this is R30 diagonals data is that, and I'm going to just do that for 1,000, which was nice and fast. And then I'm going to do this, but instead of 100,000 down here, I am going to outrageously guess. Let's just do 1,000 here. I don't really know what that means, but oh, I see what's happening here. And this thing there is subtracting that 0.252 is the average. So let's go ahead and do this, and then this will give us. If I do that and I say list line plot of that, filling goes to axis, and aspect ratio goes to 1/2.5. Let's give that a try. Okay, so this claims to be okay. So there's one bug with this, which is this is based on the fact that this sort of line between order and chaos is moving at 0.252 steps, and I don't think so. That's not right. So what we have to do is to say first of hash 2. Yes, so that number isn't quite right. So what we have to set it up, because at this time it's not. Well, okay, I'll tell you what we're going to do here is we're going to put something into our data repository that is exactly that result, r30periods.m. So let me see whether I can find that actual file from long ago. And actually that will tell us when this thing was created. So let me go there, and I'm going to go in back here. I'm going to go, I'm now looking back at my old file system. This should be, where is it now? It is in book layout results, book layout results, and now this is chapter 02. See, I was at least slightly organized back in the day. All right, now this should be what is this now? This is called r30periods.m. Amazing. Okay, so in fact we have exactly that data. So what we can do, we could actually put this in the data repository. We could create a okay, here's what I'm going to do. I am going to move this humpty humph. Alright, let me see. Actually, I'm wondering what this very, very old file that I see in that directory was. Oh wow, that was from a really long time ago. Okay, okay. Anyway, we have this thing called R30 periods, and it was created here. Let's show it here. Oh, well, that was last modified in 1999. So I don't actually know when this was created. I think in the 1990s is all I can really say. But let's go ahead and take that file, which is only 1.5 megabytes, and let's copy that, and I'm going to put that file. Okay, here's what I'm going to do. I'm actually going to build a data repository entry. So if I go to Other, Data Resource, and actually I want to see what's in that file. So I'm going to put that file in this directory that I have been putting everything else into here, and let me go find that. Okay, that's not quite the right one, so let me go ahead here and let me go ahead and put this in there and in let me see here. let's go and put that in there, chapter 2. Did I put this in the wrong place? Oh, I shouldn't have just said how organized I am, because I have a bad feeling that I just put this in the wrong place. Let me take a look here. Let me just see where these files are being put. Oh no, there we go. Chapter notes. Wait a second. Deployed notebooks. Deployed source notebooks. Chapter 2. Oh, that was stupid. Okay, so chapter 2. That is really kind of the wrong place. Okay, let me fix this, because that's just going to confuse everything. Okay, I have to close this file, because otherwise I'm going to mess everything up. Actually, what I'm going to do is I'm going to close several of these files. I don't have to close that one, but I do have to close this one, and I don't have to close that one. Okay, let me just check what I've got here. That's not the right thing. I'll check up here. Okay, so now what I'm going to do is I'm going to move this to where I think it should be. I don't know what on earth chapter notes is doing there. That should be under chapter 2. Okay, so oh gosh, how do I do this? I think that should be under chapter 2 notes. So let me just move it there. And there we go. Great. Okay, much better. Okay. So let's go back to our Rule 30 thing. But now in this chapter 2 notes, what I'm going to do is I'm going to have a section in chapter 2. I'm going to call this data files. And what I'm going to do is I'm going to take this thing here, this R30 periods file, and I'm going to put it in data files here. Okay? So now what I want to do is I'm going to say, let's see, notebook directory. That would be where this notebook finds itself in my file system. And then I'm going to say parent directory. Of that, and it's some long complicated thing. Now I want to say that to data files, so I think I have to say file name join, and then I say there may be a better way to do this. Data files. Oops, I think I need to do that. There's probably a better way to do this, but anyway, so now I say so now if I say get that thing, that will now get my, oh come on, what did I do wrong? Deployed source notebooks, chapter 2 data files. Okay, what did I do wrong here? I should say R30 periods dot m. Okay, there we go. Alright, so this is now, so let me find out what that is. That is a thing of length 3. Okay, that's interesting. Alright, so let's take a look at what, let's find out what the length of each element of that is. Oh wow. Okay, very interesting. So this appears to be 3 elements that correspond to different aspects of this fluctuation thing. So let's find out what the last one is fairly small, so let's say last to %302. I wonder what that is. Alright, when in doubt, look at the code. What the heck is it doing here? this is going to save, what this code did here is it saved R30 diagonal data What did that do? So that took that, I see, R30 boundary. Alright, so whatever R30 boundary gave us, so if I say R30 boundary of 100, that's now going to give us something. Now what is that? What is that? I wonder what that is. It's lovely that, unfortunately, this is brilliantly uncommented code from antiquity, so to speak. Okay, so let's see if we can figure out what this is. What would I have done if I had done this? I am guessing that this tells us how far it moves. What do you think those are? R30 diagonals data. So here's what I think that must be. So if we look back at this picture over here, there are these diagonals, okay? And what I'm thinking is that, actually, you know what? When in doubt, also look at what the actual book said. Yes, okay, here we go. So let's read this. The left-hand side of the pattern, blah, 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 along a diagonal n cells in, the period can be at most 2 to the n. Okay. Look at this, look at this, look at this. Period 2, Well, what I was thinking was that is the period of a certain depth, but that doesn't seem to make sense. Let me see. So if I take this, and let me just try and find out where, let me plot that. I don't know whether that's going to be very instructive. Nope. Humph. Okay, let me see. Alright. Period 2 is first achieved at depth 3. So I wonder whether there's any evidence of something like that. Oh, this might be period 2 first being achieved at depth 3. Let's see whether period 4 depth 8. Okay, well let's take the first element here. That might be what this is doing. That might be what this is saying. Okay, so that might be giving us the periods at different depths. Okay, so let's say, let's do this. Let's say first of R30 boundary of 100, let's say. And so now let me just take the last element of each of those. Okay, so now let's see whether this agrees. So this is, we claim this might be periods as a function of depth. But I don't know what the first number is here. The second number appears to be, let's take a look at where, so this claims that, so depth 8 at position 29. So let's say position in that line 309, a position of 8 is, okay, so we're off by 1, but the first position there, the first position of that is indeed at 29. So okay, so this appears to be, except that it's off by 1, this is, oh yeah, but it started 0 there. That's the periods at different depths. Okay, so the second element there appears to be, second element in these pairs is the period at a given depth. Okay, so now that's that. Now I wonder what those other numbers are. So let's take those other numbers. So let's take first slash at percent 308. And let's see, let me see. So that is, I wonder what those numbers are. Well, I'm guessing that those might be the numbers at which things first started repeating, and I actually think this old code was really inefficient at figuring this out. So if what we're trying to do is we're trying to find the boundary between order and chaos in this picture. And so what we need to do is to find those diagonals, and then for each diagonal we need to figure out where it stops repeating. So I'm reckoning, let's just try doing a direct approach at that. So we can get those diagonals by saying, let's try 100 here. So what is one of those diagonals? So what we need to do is, this is going to be a whole array. Let's do it just for 10 and see what we can do with that. Okay, so this is a grid of values, and what I want to get is the diagonal on this side. So I want to be slicing off parts of this array, and let's see, how would I do that? I think, let me see here. So let's go back here, and I'm trying to work out how to extract that diagonal from this this thing. You know, it's really weird. I was doing this very recently for a really weird reason, which is that Rule 30 picture shows up in, oh, you know what? I might actually have the code here. There's this train station in Cambridge, England, that uses the Rule 30 pattern, and look at that Rule 30 pattern, and it okay, there's a photograph, but it tips it on its side like that. And if I am super lucky, no. Okay, I'm actually showing the thing tipped here. I'm not extracting the values from. I should have been. So this is showing a slice from the side. But what I want to do is I want to extract these values, and I'm feeling stupid about this. What I want to do is the first row here. I want to let's just find out what the size of that grid is. So the dimensions of the grid. Oops, that's not what I wanted. Kill that. Dimensions of that grid. Okay, so it's an 11 by 21 grid. So what I want to do is I want to get line. I want to be taking out. You know, I bet this is in that old code here. I bet that's in the old code. Oh, that's clever. All right. What that's doing is, okay, you know what? I've got a good idea here. So what that old code is doing is it's saying, let's just rotate this around. So let's say that the nth position, so I want to go ahead and say map indexed, and then I want to say rotate left, I think, onto this, and let me just see what happens if I do that. Okay, so what that should be doing, except I may have goosed it up completely, is, did that do the right thing, or did that do utterly the wrong thing? I'm trying to shift that guy. What I want to do is I want to say rotate left #1 and #2 let me just try living really dangerously, and let's say 21 minus hash 2. Oops, minus hash 2 there. And I have this suspicion that that might do something useful. And I'm utterly wrong and confused. Let's just try being totally crazy, and let's use rotate right instead. Oh no, 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 no. Let's see, first of hash 2, let's try that. Oh, come on. What I'm trying to do is I'm trying to line it up so that the leftmost, why isn't that working? What I want to do is the first line, okay, well let's just try it by hand. So I'm taking this thing, and I'm taking the first row of this thing, and I'm saying rotate left that thing by 21 positions. Oh, silly me. Silly me. I want to say that will be by 10 positions. Okay, that looks a lot better. Maybe it should be 11 positions. Okay, there we go. So what I've now done is I've taken that pattern and I have made it so that the columns, those things here are shifted around so that they're vertical. Okay, I'm going to try this again, and I'm going to try this for a bigger picture, and I'm going to see whether it's successfully. Okay, so let's do it for 100 steps here, and that will then become 101, and then let's make an array plot of that, and let's see whether it successfully made this be vertical. Okay, terrific. Okay, so now what we have to do is every vertical column here, we just need to know when does it become periodic, and that will tell us exactly the position of that center line. So now very conveniently in modern times there is a function called find transient repeat, and let's see. So what we want to do here is following is the original code used in the creation of the book. Okay. Let's see, modern code, and let's go ahead. So this thing here, we would say create a shifted version of the Rule 30 pattern. Oops, what did I just do wrong here? There we go. Okay, now every vertical column here, so what I want to do is I want to simply extract the, so let's go ahead, and that will be the first column. So in order to get the first column, I would take this, and I would say let's just do it for the case of, let's do it for 20 or something here. So this is 21, and then what I would do is I would transpose that, and let's see what I get if I do that, and then I can do an array plot again, and I think I will have the right thing there. Is that right? That should show, yes, every column has become a row now. Okay, so then for this, what I want to do is I just want to say find transient repeat, and let's say I want to find, let's say I want to insist that things repeat at least 3 times. Okay, actually I'm going to need to say this. That, comma 3, there we go. Okay, so what this is going to do, this is going to find that first row, that first column repeats with period 1 very quickly. Okay, so this is now showing what the transient length is and then what the repeats are. Okay, so now let's do this for a slightly larger case. Let's do this for 101. And then what we're going to do, so that this is now going to find those. And now for each of these, what I want to do is I want to say length of last of that, and that will give me the period. Okay, so those are now the periods of every one of these. Okay, so now and if I say here position of that, comma 8, I should indeed get that position 30. That's terrific. Okay, now the zeros here come because it never found a repeat. Okay, so I think what we want to do here is let me see what happens if I go much further here. I'm going to say transient repeat 2. I'm going to say I only require that it repeats twice to know that it was a repeat. And let me go ahead and live it a little bit dangerously here and do this for 1,000. So that may take a little while. Okay, and now let's do this. Okay, terrific. So this is now giving us the periods that it can determine. So some of these periods it can't determine. And what we now want to do, okay, so now shifted version of the first 100 steps in the Rule 30 pattern. And now what I'm going to do here, let's do this, and let's just say okay, so now I want to say length of last of that. Not what I wanted to do. Let's see what happens here. What happens here? There we go. Okay. Okay, so this is lengths of repeated periods as for successive depths in the pattern. So 0 indicates that no periodic part was found. Okay, so now here, this is, okay, so it's probably only meaningful up to a certain depth here. So let's find out what that depth is, and I'm guessing that what we want is to say position in there of 8, flatten it out, and the last one of those is 60. So I'm kind of guessing that the only meaningful, it's probably only meaningful up to the depth 60 here. So at least for those, at least up to depth 60, let's look at the lengths of the transients. So if we look at the transient, part of the transient is going to just be the white space here. Okay, so there's a little bit of tricky geometry here, because what we have to do is figure out what the rotated version of this is. And I'm getting tired, and I think I'm going to be less effective here. So I'm actually going to put a big note saying that this section is unfinished, and I'm going to make that big, 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 and I'm going to put a bright yellow background, yellow, there we go, background behind it, so that I know that isn't done. And I'm going to see if there's one more easy thing to do. Let's see if there's one more easy thing to do. That may be horrifically difficult. So these are pictures of samples of ornamental art. Let me just see. Okay, I'm just going to try, just for fun, before I go to sleep here, to make those pictures. Let's see whether I have those in the antique code. So let's see. Let me see what that would be. That might be Cretan, because I think that is the maze. That is the construction of the maze of the Minotaur. Well, maybe. it's supposed to be the maze of the Minotaur, but let's make this okay, so that was called ornamental art, but I think I got it in the wrong place here, so let me go ahead and put it in the right place. Deployed notebooks, chapter 2, notes, and that was called ornamental art. Okay, and let's say this is Greek, whoops, not green, Greek paren Cretan maze. Okay, well, let's just try living absolutely boringly. Oh wow, what a mess. Alright, let's try see whether the antique code, let's just pull it in here, and let's just see. Wow, this is all in. Okay, let's just try one of these graphics things. This is horrific. Okay, let's just try one here. Well, alright, you know what? I'm just going to try doing something totally outrageous. I'm going to, let's take that show, and let's just see if it just runs. Wow! That's amazing! That's code from 25 years ago and it just runs. Wow! It's not the most beautiful code, to put it mildly. I wonder if we can do anything to clean this code up. I mean, look at that horrific thing. It's got plot ranges, explicit plot ranges, and so on. What a mess! But at least it just runs. That's kind of exciting, actually. Let's see if I can see anything about this code that is. Well, I've got lines of thickness 0.25. Let's see if we can get rid of those at least, because that seems really kind of. That was probably done for when the thing was printed. Let me just, because that was 0.25 of a printer's point thick. So let's try and get rid of that. Let me just see what happens here. Let me just get rid of those absolute thickness of whatever, and let me go ahead. Where were they? There was another one there. This is probably going to, maybe it's going to make a big mess if I do this. Okay, another one there and another one there. Well, it looks kind of fine too. Well, that's totally weird. Why is the border of that one grey and the borders of the other ones are... Did I goof up here? Did I goof up? Is there an absolute... Oh, there's a hiding absolute thickness. Well, you know what that was. That was the... Oh, I see. That was for the border. That weird thing was the border. Oh. So what I actually want to do, let's just try putting in grey. There. I think that'll be more beautiful. Okay, so that was for the border of those things. So that's really a weird thing. So actually I'm going to leave it because I don't really see the point of changing that. And well, at the very least, okay, there. This is pretty ugly code, but I think that's what one's going to need in order to make that pattern. Because that's kind of an arbitrary pattern that was kind of created by, I don't know, King, what was his name? The dad of Theseus. I don't remember what his name was, but anyway, the plan of labyrinth housing the Minotaur in the palace of Knossos in Crete. You know, I've always meant to go to Crete. I've never been to Crete. So something it's on my list. I wonder whether one can. Okay, let's try the next thing here. That is a Celtic pattern. So let me see whether I can. Let's see whether that works. See whether we're really lucky. Okay, that is Celtic pattern. Greek maze pattern. This was made between 50 BC and 50 AD. Alright, let's see whether we can... Wow, line erasure finished object. Whatever that is. Alright, let's see. Oh wow, this is going to be a mess. But let's try it anyway. Well, that's an interesting strategy for not having the code look as horrific, is to make it smaller. What did I just do there? Did I copy all of them? Did I not copy all of them? That was weird. Let me just try copying the whole section here. Okay, that copied all of them. And now, well, let's look at the first one. This is so small. Okay, here we can get rid of the smallness in one fell swoop here. Hold on one second. Let us say for all of the drat, I erase that. Let me go ahead here, and so I can say clear formatting. Ta-da! There we go. Okay, well that is a singularly uninspiring thing here. Celt 1, Celt 2, Celt 3, Celt 4. Okay, to just make me feel better, I am going to at least make this first element of Celt. Okay, and let's just go ahead and do that. Oh, silly me. Silly me, silly me, silly me. Let me clear Celt, and then let me say Celt of 1. That's the first Celt thingy. And then I'm going to do that. That's the first Celt thingy. And now Celt of 2 is the second Celt thingy. Oops. Celt of 2 is the second Celt thingy. Celt of 3 is the third Celt thingy. This is not super exciting, but hopefully, and we're about to find out whether all these Celt thingies actually add up to something. Alright, Celt 5 and Celt 6. Alright, and then what I'm going to do, let us try the following thing. So, I don't even know what any of these are, but let's try making the first one, let's say line of Celt 1, and let's make a graphics of that, and let's see whether it looks anything like what we want it to look like. Aha! Fascinating! Okay. Alright, let's go ahead and just make a table of all the Celt thingies, and let's see what it does. Let's see what it looks like. N up to 6, oops, comma, N up to 6. So this is now going to make something which combines all those. Oh, that's very encouraging. Okay, that's very, very encouraging. So that looks like that third picture there. So now the question is, what on earth do we do to make the other pictures? Initial circles, but where is the definition? Help! Where's the definition? Don't say we've lost the definition. Well, that's bad. It doesn't seem to be here. I wonder what these weird things are. Oh, no, 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 I know what this is. Oh, wow. Oh, wow, oh, wow, oh, wow. This is, watch this. There's going to be magic here. Well, a certain kind of magic at least. That thing which looked like a bug, I think if I go ahead and say remove clear formatting, I think we are going to discover, no, what are we doing here? So this, see, I think this thing is going to turn out to be, crazily enough, let's take a look. What the heck is that? See, I think that's a piece of, I think that's some input code that was made very, very small, but somebody may have goofed and not stored it in the file. That somebody might have been me. Well, I wonder where we can find that. I wonder whether I've got that in another directory. Okay, so there's a mystery there. So something is missing there. Let me just see if there's anything up at the top here in the initialization that might help us. Nope. Okay, that's not a good sign. Well, That is not good. We at least had something reasonable here. Alright, so I'm going to make a note here. I am going to say let's see here. I'm going to make something down here. And let's see, I should be able to close that up. Okay. Polygonal data picture. But now something is horribly missing. Okay. Some data is missing, apparently. So that we have to go on a little bit of a hunt for. And let's go ahead and format that with background color of yellow. And okay, we're on a bit of a roll. Let's just see if we can do a couple more of these. What is that one? Roman. See what that one looks like. See whether I have that here. Let's see what Roman is about. Oh my, Roman is complicated. Whatever Roman is, it's complicated. Let's just see if, once again, we are lucky and let's see, we say Roman pattern. What is this? That looks really weird. Well, let's just try doing this. Once again, let's try just running code from 25 years ago and see if it just works. I don't know what that does, but anyway, let's just try this and see. This is kind of complicated, isn't it? Alright, I could have just selected all of them and say just run this. That's not what I wanted at all. Okay. Alright, this thing here well, I can get rid of that and I can just say graphics row. Let me not bother with the 0.25 there. Oh, amazing! Wow! It just runs. Spectacular. Well, that's cool. Well, I don't know what it's doing, but all that code just ran. Now I think this is, again, we've got that goofy thing with the absolute thickness 0.25, which was set up for when this was printed, and I just don't think we need those. But the good news is this just ran. So okay, I'm getting less. Let's just see what else there is here. I'm really now keen to just see if I can get through these and see whether the other ones just run. Okay, so that is the let's say that is just code, and then this is picture. I'm being a little sloppy here because I'm not really explaining what's going on. Okay, so there's the code and there's the picture. Wow, it's kind of cute actually. It's some kind of Fibonacci, I mean some kind of phyllotaxis spiral type thing there. Probably has the golden ratio embedded somewhere inside that. And I'm not finding a golden ratio here, but I'm kind of thinking that these numbers, that some ratio of those numbers is a golden ratio, or an approximation to a golden ratio. Anyway, alright, let's just see whether we can find that pattern there, see whether that still survives after all these years. That is a Cosmati pattern, I recognize it, and let's see. Okay, let's try our luck here. Alright, let's see. Oh my gosh, there's just a ton of stuff here. Okay, let's say Cosmati pattern. Alright, let's just be crazy and just select them all and just see. Oh my gosh, it's full of lots of detailed stuff. I mean, I think I'm sure we don't need this anymore, because I'm sure that, okay, we certainly don't need that, because that was running a, oh, this is part of, oops, what this was part of the computation. That was part of the computation that was done up there. Okay, so now let's try picture, actually really pictures. Okay, let's see what happens. Again, a little scared doing this after all these years. Let's see. Come on. Ah, amazing! Wow. It's kind of like going into an archive space and starting to just sort of pull things out of the archives. It's really kind of cool. Actually, let me just, for fun, let me just look at that Cosmati 5. Let me look at it bigger. See whether it's oh yeah, that's cool. Now the fact that it had to have all those weird numbers that computed things, that's kind of disappointing. But the fact that all this code just runs, yeah, well, this is what happens when you try and maintain compatibility in a language for a long period of time. The code from 25 years ago just runs. It's kind of exciting. Wow. All right, I'm just so much on a roll here. I have to just try. Let me just see whether that this thing here doesn't seem to be in there. Let's see. That is a I mean, that pattern was just made by a human, so to speak. That wasn't made by that's it's a piece of calligraphy. It's a piece of Islamic calligraphy. And you know, I thought when I first saw this, I thought, my gosh, that's a mathematically computed thing, and it's, you know, you find it on some wall at some at a place in Iran. But it turns out it's a kind of a weird square rendering of a verse from the Quran. So it's not something just computed from a math function. All right, let's just try. Oh, look at that! We have a thing from. Okay, one more thing we're going to try doing here. He says, and that's that picture of that rope. I cannot believe that's actually going to work, but I'm going to just see, just because we've been doing so well here. Okay, so this is called the concept of rules, and that is another piece of notes. The concept of rules, and let's just see. Oh gosh, it's another immensely complicated piece of code. All right, let's try it. Again, I'm sure it doesn't need to be as complicated anymore. I'm sure there are a lot more powerful built-in functions that we now have, but let's try. Okay, let's see. All right, let us live dangerously again. Oh my God, this is so complicated. How can it need to be this complicated? Come on, just run. Don't do anything crazy. What is it doing? Oh, so sad. All right, let's take a look at what this did. You know what? That show definitely doesn't belong anymore. Graphics 3D mapped over. Oh, this is completely crazy. That is from when this used to plot. That would have worked on some kind of tectronics. Okay, let's try putting that show back in again. That was from when you had to like show displays on a tectronic scope or something. Okay, well that wasn't very good either. But let me just see. I'm pretty sure I know how to do this. Why would I need to do it that way? Let's see. that should be, I think I should just be able to put that guy in here. Let's see what happens if I do that. And then I think I can get rid of that and can do that. Well, let's get rid of all this junk. Oh. All right. Let me see. First, flat central wires too. I don't know why we're doing it that way, but let's go try and find out. So this is. I'm going to try and get rid of all of that. See what that does. Not a good sign. Graphics. Okay, let's try something here. So central wires sub 2. What the heck is that? Well, that's not a good sign. That's not a good sign at all. Okay, where is central wires? Oh. I goofed here. I didn't realize what it was doing. Okay, so let's go back up here. What this was doing, like that, oh gosh, all these display function to something weird things absolutely have to be removed. That is what, and that doesn't help there. That's something that was defined specifically for the book. Okay, so let's look for this display function thing. That came from an ancient world in which displaying graphics worked differently. So I think we just remove that display function to identity. And then, in fact, if we do this, that's a bit disappointing that that doesn't show anything. It's not a very good sign. Plot points. Well, that's not a good sign. Let me see. So, well, you know, this is very weird because right here is an actual picture of our wiry thing. But you know what? I'm going to get rid of, every time it says display function, I'm going to get rid of it because I think this is past my bedtime, so maybe I will not succeed in this. But let's try here. What is that doing? Get rid of that. That makes it look nicer at least. Okay, here we go, another one of those horrible things. Let's just try that again and see whether it produces anything. You know, it's a very bad sign that there's no graphic in those, but we're going to figure that out in a minute. Okay, let's read some code from the top. Okay, there's a bunch of weird stuff there. It's making tables and circles and who knows what else there, circles and disks. Okay, so let's now say pick 2D. Well, let's just see what pick 2D of 3 is. Okay. Oh, there's a thing called hairline style, which appears to have gotten itself in there. Let's see, where was that? That we probably want to get rid of there. Okay. So this is a good sign. So pick 2D does appear to be a picture of that interior thing. And actually even that case, so in fact, probably, let's see how this works. So down here somewhere, something was goofy there. So we can say, if we say here, table pick 2D of n goes from 1 to 3, I reckon, oh yeah, very nice. So that shows those cross sections. So this is actually, this picture is about how rope is made. And so these are cross sections of ropes apparently. Okay, so that's a good sign. So that's pick 2D. So now central wires is R1 times cosine phi. Let's see what R1 is. R1 is 1. Okay, that's pretty civilized. So let's just see why this isn't working. I bet we don't need that plot points thing. I think that's a waste of time in modern world. So let's see what this is coming out with. Okay, what did we do wrong? So what is h? H is 30. Phi goes up to 0 to 2 pi. And R1 is 1. So this is 1 times... What is that? Gray level 0.3. Okay, well let's just try this. This is a simple parametric plot, so why is this not working? Okay, so let's take a look at what that thing actually is in the middle there. Okay, so evaluate that. Oops. We get this thing with that weird gray level. I wonder what that gray level is doing. Maybe that gray level is wrong. Let's get rid of that. Aha! Well, that's interesting. All right. So that might be the center wire in this thing. So let's try this. Okay, so let's try getting rid of that gray level. So central wires, again, I don't know what it's doing to get rid of the gray level, but I'm going to do it anyway. Central wire 0 is that. Okay. Now let's try down here. What on earth is this thing here? Well, I'm a little bit confused by that. Let us try looking up parametric plot 3D and see whether it in fact does allow a gray level there. Maybe it once did and no longer does. Maybe that was an undocumented feature of 25 years ago. Yeah, it doesn't show it allowing a gray level, so let's get rid of that gray level thingy. I don't know whether that's really the right thing to do, but we'll try it. Okay, so let's get rid of that whole gray level thing. Oh dear. Okay, let's see, gray level. And I'm going to get rid of that plot points thing as well because I don't think it's needed. Okay. It's a little bit weird that we didn't see any output from this. Oh, I see why we don't see any output. Okay, so actually if I change that to table here, we should see a bunch of wires being created. Okay, that's a good sign. So those are little wiggly pieces of the wire. So now let's try central wires 1 is that. I'm going to get rid of the plot points thing because I don't think we need it. You know, this is incredibly obscurely done because, oh okay, and I need to get rid of that gray level 0.3 there. Okay, let's get rid of the plot points. Nowadays there's a tube primitive which allows you to just specify things as a tube. But let's see if we can get this working anyway. Okay, all kinds of weird stuff here. What on earth is that? Well, I think that's probably stupid, but we'll do it anyway. Okay, so let's see what central wires 2 actually is. What on earth is this? Oh my gosh. It's full of random pieces of wire, he says. Well, except that coordinate... Oh, well something went crazily wrong when we did this weird substitution here, which I don't even believe in. What on earth is that doing? Polygon of L is polygon of G of whatever. Hard to know what that is. You know, I think maybe we're just going to have to declare victory here, or at least not really victory, but declare something. Look at this weird stuff. I wonder what all of that is. Just to see how it works nowadays, there's a function called tube, and tube, very conveniently, just makes a tube, which can be in any shape. So instead of all that weird parametric plot stuff, we just would have to make tubes. So I'm going to say this is unfinished, and I'm going to wrap up in just a moment here. Let me just put a big unfinished sign at the top here. It's gotten too late for me, so let's go. That's yellow. And well, we did some things here. So I'm pleased that we managed to make progress on chapter 2 of my book. And I think we should stop there. And so I hope anybody who's been watching has been having fun. This is a good recreational activity for me. And well, I've almost done one section of one chapter of 12 chapters. So I'll come back another time and I'll keep going. Maybe we'll finish some of these parts here. All right. So I am going to sign off if I can figure out how to do that. Bye.